When you look at any kind of work process, there's variability that creeps into that work process as to how you get it done, and you're not going to be able to get it done in exactly the same amount of time every time. You're not going to get the same result exactly the many times that you do it, and the variability is going to come from different sources. So if you were to look at the input process output model, you can think of the variability coming from different sources at the input side, which is the materials that you might use, the raw materials that you might use, and the tools that you might use to get started with the process. Within the process, who is doing it, the operator, the methods, that there may be a choice of methods to do that particular process will cause some variation. There'll be machines, and the machines might perform differently based on how well they've been maintained, or if there was something that went particularly wrong that day. And then there will be the environment. The environment could be factors such as the weather. If you're talking about a process that has a lot of human involvement, the weather might have an impact on how that process is done. So there'll be some variability coming into that from that as well. On the output side, the fact that the output needs to be measured, there might be variation coming from the measurement instrument that's being used. So if you're talking about timing something, maybe there's some variability that's that's getting into that measurement process based on how that measurement instrument is performing, how that stopwatch is performing, whether the person who was using the stopwatch used it correctly, started it at the right second, and stopped it at the right second. And then in terms of inspecting outputs, if there's inspection, then there will be some variability based on who is inspecting, and they might have different perceptions of what they're seeing in the output. So as you can see, there'll be variability coming into any process, and you can apply this idea to pretty much any process, any kind of work that you see around you, any kind of work that you even do on a day-to-day basis. So let's take an example of something that you can relate to, right? It's your daily commute to work. Wherever you go to work, it's your daily commute. And what I'd like you to do is think about the different factors that you have to keep in mind when you're asked the question, how much time do you take to get to work? If you say 15 to 20 minutes, you've already given me a range, 15 to 20 minutes, and what determines whether it's 15 or 17 or 20 minutes? So that's something that you are already thinking about. So what I'd like you to do about is think through the different sources that force you to give that range of 15 to 20 minutes or whatever time that is. And you can, I've given you a few pointers from the previous slide here. In terms, you can think about it in terms of the sources of that variability. So is it coming from the materials that you're using? Is it coming from the route that you take? Is it coming from something else? So think of these things and see what you can come up with in terms of the sources of variability for your time to commute to work every day. All right, so depending on how you commute to work, whether you take the train, whether you take the subway, whether you use your bicycle, or whether you use your car, you may have thought of different things that cause you to give an estimate of your time, which is a range. So you usually think about it in a range, and you may think about, do I have to put gas in the car? Do I have my train pass? Does it have enough money, or am I having to stop at the window? If it's my bicycle, do I have to fill air in the tires before I can take off that particular morning? And that's going to impact the time that I take to get to work that particular day. You could think about environmental factors, and those will have a big factor, will have a big effect. So for example, if it's raining that day or snowing that day, and if it's a particularly high traffic day for any particular reason, that's going to have an impact on your estimate of the time that it takes. And some of this is going to be, well, it'll depend on whether I get all green lights or I get all reds, and that might be a matter of chance for that particular day. There might be also some variability that might be coming into this based on who's driving if you're carpooling. So that might be the factor that is causing variability. And then what will also cause variability is, depending on who's driving, how well are they at obeying the traffic rules, so that might have an impact on how fast you can get there. So what you can see here is that variability can come from many different sources. Now, when you think about variability, what you can also do is think about what is the normal course of events that can occur when you're going to work, and what is abnormal. So what we're talking about here is that you might say it takes 10 to 15 minutes, depending on traffic, depending on getting the lights in the right sequence, and those kinds of things. And that's something that factors into your normal course of events. Now, if you happen to have an accident on the road that day, and you get stuck in the middle of two cars, and you're not able to move out of there for an hour or so, you're basically talking about something that you don't factor into your daily estimate. So if I were to ask you how much time does it take, you're not going to take that kind of an event into account when you're talking about an estimate of your time. So that's how we distinguish between these two kinds of variability, called common cause variability and special cause variability. So what is common cause variability? It is the variability that is expected in your process based on your current way of doing that process, your current way of doing that work. It exists. It's a measure of the potential of that process. Doing the process in the current way, in the current steps that you're following, it is expected that you will take so much time, or that the quality level is going to be something that you expect. So that's the variation that is coming from common causes, things that are expected to happen. And special causes are things that are beyond common causes. So things that you do not expect to happen, they come from things that are completely outside the process, and that is the variation that is beyond what is the inherent capability of the process. Right? So here's the difference between these two. But I also want to caution you that you can think about any particular cause, and there might be a fine line between either including it in common or special cause. Right? So what do we mean by that? Do I want to include some special events in common cause? Do I want to include the fact that I did not have gas in my car that day in the common cause, and I want to include that factor in having to go and put gas in the car if I'm thinking of the commute to work as something that occurs normally, so that's a common cause. So there's some fungibility in that. You're able to make changes to common and special cause based on that. So it's your definition of common and special cause in that way. All right, so let's turn to this idea of statistical process control, and this is the underlying idea behind this is to use statistics to be able to distinguish between common and special cause variation, right? So it's to be able to distinguish what the inherent capability of the process is, and then once you've established the inherent capability of the process based on some statistical principles, to be able to use that to monitor the process. So you figured out that it should take you 10 to 15 minutes to get to work. You can time yourself every day, and it should be between 10 to 15 minutes, right? So that gives you your established inherent capability. And then if it goes above 15, you say, well, what happened that day? And what is something that was a special cause that day, because it normally takes me 10 to 15. And on the other side, if it goes to 8 minutes, you say, well, that's something that's a pleasant surprise. Why did that happen? What was the good luck thing that happened that day? And then you might want to think about, well, can I make some changes in order to move towards that 8-minute time, so that I can actually reduce the time that it takes. So statistical process control charts serve this dual purpose of establishing the inherent capability of the process and telling you when your process has given you performance beyond the inherent capability, right? How do we do this? We do this based on making control charts. So when you talk about making control charts, and you as a manager is going to establish the inherent capability of the process, the first step is going to be developing the control chart. Right, so you're going to come up with that band that's going to say this is the normal capability of this process. How do you do this? To get started with this, you choose what kind of measurement you're going to use. Right? And we'll talk about a few types of measurement as we move along. And what do we mean by choose what type of measurement? Are you going to choose a measurement that's simply going to tell you this is a good product versus a bad product, this is a good time versus a bad time, or is it going to be more specific? Now, why is it important to choose measurements? It's because based on what measurement you choose, you can use a different type of process control chart, right? Why is it good to have this choice of different types of process control charts? As you will see later, there are advantages and disadvantages of choosing certain types of measurements and certain types of process control charts. Nevertheless, the idea of preparing a control chart is you have to choose what kind of data you're going to use. In statistical terms, we're saying what kind of distributions of data are you going to use to make your statistical process control chart. You have to also choose your data collection plan, which means how often will you collect data, what is going to be the size of your sample whenever you collect data. Once you've collected your data based on that data collection plan and that sample that you've collected, you're going to calculate some statistics. And the main statistics that we'll be using here are the mean and standard deviation. Now, the mean and standard deviation are going to be computed differently for different types of distribution. So this goes back to the idea of you have to think about what kind of data you are going to use in order to come up with the statistical process control chart. Next step you're going to do is you're going to make the actual control chart. You're going to come up with the upper and the lower control limit, what we call the UCL and the LCL, and there's going to be a center line based on the average that you find. That's going to say this is the average, and this is as high as you can go and call it a process in control, and this is as low as you can go and call it a process in control, and that gives you the width of the inherent capability of your process. I call this trial control limits here because when you as a manager are at the point of making that control chart, you are basically calibrating an instrument. You're coming up with an instrument and you want to make sure that that instrument is something that is good and reliable, right? You want a good instrument that you as a manager can use in the future, that you can give to your frontline people and say, under normal circumstances, this is what you should get from this process, right? And the reason to call it trial control limits is if in the process of coming up with these control limits, you find that there are points outside of the control limits, right? So you make the control chart and then you go back and you plot the points that you had used to come up with these control limits, and you find points outside of the control limits. It's basically telling you that you cannot really rely on these control limits, right? You have a process that's already out of statistical control, and you are using the measurements from that out of control statistical process to come up with your calibration of upper and lower control limits, and that's simply not going to work. It's not a reliable upper and lower control limit. So there, what you have to do then is you have to go back a step and say, if there's a single point that was outside of the control limits when I calibrated it, if you can figure out what happened at that point, if that was a special cause that you do not want to include, you might simply just throw off that data point, that sample, and then recompute the control limits. But if you can't really figure out what the cause was and it seems to be a mystery, then you might have to simply collect new data. And the idea is that you are calibrating a control chart when the process is performing normally, quote unquote normally, which is quote unquote given the current conditions, this is how it should be performing. Because remember, you're trying to get at the inherent capability of the process. So once you've come up with the upper and lower control limits, once you've calibrated the control chart, the next step is for you as a manager to give it to somebody in the front line and them being able to use it, or for you to use this control chart to keep an eye on the future performance of your process, right? So you've calibrated it, now you've locked in the upper and lower control limits, and now you take daily samples from your process and you plot them, right? So you take them at predetermined intervals. You might say, I'm going to take 5 samples every day, or you might say I'm going to take a sample every hour, every day, and each sample is going to be of size X. Could be 5, could be 10, whatever that you've chosen. So you do that, you collect the data, and you plot it on the control chart, and then you go and see if there is a point that's outside of the control limits, right? So you plot the points, and as you plot the points, you look for points that are outside the control limits. If you find a point that's outside the control limits, what is that telling you? It's telling you something happened that made this process go beyond its inherent capability. Now, you would think that that's necessarily a bad thing. It's gone beyond its inherent capability. Yes, it may be a bad thing, or it may be something good that happened. What do I mean by that? It's not necessary that when there's something outside of the control limits, that it's a negative thing that happened, especially when you're looking at something like proportion of defects, right? So if you think about a control chart for proportion of defects, if there's a point outside the control limit on the lower side, that's telling you your proportion of defects was lower than you anticipate in the normal course of events, which might be a good thing. So what all we can say when there's a point outside of control limits is there's something that has happened that's worth going and looking at. So go see is what a point outside the control limit tells us. And then finally, when you go see, you may be able to take action based on what you find there. But finally, what you want to do is, if you do find a lot of points going outside the control limit, you want to do something about it, right? You want to improve the process so that there are no points outside the control limit. But also, more importantly, what that's also telling you is to recalibrate your control limits. So if you're finding too many points outside, it's saying that maybe there's something that's changed in the process that you need to recalibrate your control limits. And on the other extreme, we can look at patterns that will tell you something even when there's a point that's not outside the control limits, even when there's not a single point outside the control limits. So we'll look at those kind of patterns later, but before that, let's just get a sense of the general structure of control charts. So any control chart will have these three lines called the upper control limit, the center line, and the lower control limit. The center line is going to be some sort of a process average. The upper and lower control limits are going to be based on 3 standard deviations above and 3 standard deviations below the process average. And once you've calibrated this kind of a control chart, you will plot the samples. You will take the samples from that process and you will plot them in chronological order going left to right. The idea being that you're looking for points outside of the control limits, but you're also looking for any kind of pattern that you might see in this control chart, even if there is not a single point outside of the control limit. So to put some specifics on the kinds of patterns that that might be worth going and looking into. Now, this is not something that has a statistical principle behind it. It's going to be more context specific. So based on what your context is and what that process control chart is all about, you might find something that might be worth looking into or not. So the first one that you see over here is if there's a sudden shift in the point clusters, right? You had all the points in random fashion within the control limits all this time, and there seems to be a sudden shift either upward or downward towards the upper control limit or the lower control limit, and there seems to be a concentration going one side or the other. That could be a sign that's telling you something. If there's a cycling of points, right? If the points are are all below the center line towards the lower control limit, and then subsequently they're all above the center line, and then they're towards the upper control limit. Next, again, they're down towards the lower control limit, lower than the center line, and this cycle keeps on continuing. That may be telling you something. So in this particular example, it might be telling you that there are 2 different distributions here, right? You might want to think about separating out the data for those 2 different distributions. This might be the idea that there are 2 different operators that are working on this task at 2 different times, and this is showing you that they're performing differently. So that might be information that might be useful in terms of either coming up with 2 different control charts for them, or saying that, well, one of them is doing a good job and one is not, so let's do something about this and try to get this to be the same. Trends, similar idea to sudden shift in point clusters. If there's a trend of points going towards one side, it's telling you that even if a process seems to be within statistical control at this point, it's heading towards going out of control. If you find all the points are concentrated at the center line, you have an upper control limit and a lower control limit, and you find that the points are all very close to the center line all the time, what it's probably telling you is that there's less variability than you expect in this process, that the process has actually become much more predictable, right? So it's time to recalibrate the control limits and use a new process control chart with new control limits. So these are some of the things that you might want to look at in addition to looking for points outside of the control limits in a control chart. Where does this whole idea of plus or minus 3 standard deviations come from? Now, some of you may already be familiar with this. The idea is coming from what we know as the bell curve, the standard normal distribution, and it's the idea that 99.7% of the observations are going to be within plus or minus 3 standard deviations. So that's the idea that we're using, that's the idea that's being used in statistical process control, that under normal circumstances, and that's quote-unquote normal circumstances, a process reflects what is seen as the normal distribution. Plus or minus 3 standard deviations will cover 99.7% of observations. So what you have here is a schematic that's showing you different types of control charts that can be used. Broadly speaking, we can take measurements based on attributes and variables. What are attributes? Attributes are things that you can count. Attributes are things that you can see in terms of something being good or bad. In statistical terms, you're talking about discrete distributions there. So attribute control charts are going to be based on discrete kind of distribution data. So like I said, there are many types of control charts that you can use. And within the attribute control charts, within the attribute type of control charts, you can have many different types of charts. What I have described over here, what you're seeing over here is that the P chart is the one for if you're looking at proportion defective. So the P stands for proportion, and if you're looking at the number of defectives in a process, you're simply interested in looking at whether a product is defective or non-defective, you would use what is called a P chart. The other kind of attribute chart that is commonly used is called a C chart, and a C chart is used for defects. So if you are interested in the number of defects in a particular sample of products, you would use a C chart, and the C there stands for count. And there are several other types of attribute control charts. On the other side, you have the variable type of control charts, and these are based on continuous distributions. So distributions where the decimal points have meaning, right? You're talking about length, weight, you're talking about viscosity of a liquid. Those are the kinds of things that you can actually measure. So this is going beyond saying I'm counting the defects or I'm looking at whether a product is defective or not. A variable control chart is actually looking at a particular aspect of that product or process and actually measuring it. So here what we've depicted, or what you're seeing, is the XR chart. The X stands for mean and the R stands for range. So the XR chart, or the X bar R chart is how it is known, is one that's looking at the mean and the range and using those to come up with inherent capability of the process, and then to use it further for looking at whether the process is in statistical control. So in this lesson, what we'll do is we'll look at these 3 different types of charts, the P chart and the C chart and the XR chart, and we'll go through the mechanics of each one of these as in terms of how these are constructed and used, knowing that there are many other types of charts out there that you can go and select from.